we're going to be working through the proof that we're describing here. We're going to prove that the centroid of the triangle ABC that we have in our diagram from the origin, which we have describing here as our origin, is given by a certain expression, and I'll bring that expression up shortly. Now, geometric proofs of a triangle, this is going to involve a few parts that we're going to work through carefully. So, first off, let's look at defining some things about the triangle in terms of vectors. So we have this, okay, so this is from B to A, is based on position vectors, O to A and O to B. And we've got B to C going this way, and we've got A to C, so this side coming down here. Okay, so that's the first thing. Define the sides of your triangle relative to the vectors. These are each vector O to A, O to B, and O to C. They are these extra vector line segments that I've just drawn in here, all coming from the origin. Okay, now just to make it more simple, we're going to make O to A called vector A, O to B called vector B, and O to C is vector C. So then what else we could say is we can define midpoints on our triangle. We're going to call that midpoint M, N, and P. Okay, now at each midpoint we have some information about the vector. We're going for looking at the first one from B to vector M. Well, that's half of B to C, and B to C is given by this vector expression here. So by simplifying, I get this bit of expression for the midpoint. We could say the other things about B to P. So going from B going to P, well, it's half of B to A. And finally, something about A to N. So A to N, well, that's half of A to C. And we can simplify it in terms of vectors A, B, and C from the origin, the position vectors. Now, in doing this proof, in defining the centroid of a triangle, ABC, this one here, we're after the position vector of O to G. This dot here, G, is your centroid. And it involves the assumption that the medians of the triangle, okay, now the median is the line originating from the vertice and intersecting right across the opposite midpoint. So this here is a median, this is the median from vertice C to midpoint P, and so on. All these medians are concurrent, which means that they all intersect at point G, and they're all divided up in the same way. Okay, and to prove the centroid is given by this expression here. Everyone see that? It is OG is equal to a third of O to A plus O to B plus O to C. So it's just like a arithmetic mean of all three position vectors. Interesting. To prove that, we first have to prove this about the medians of the triangle. They all pass through G and are divided the same way. So that is, looking at the first one, B to G, starting at point vertice B and going to G, well, that line segment there, that's just some fraction of B to N. And C to G, C vertices C over to the centroid. Well, again, that's some fraction of C to P. And we can see that visually, but what's important is that they all have to be divided the same way, which means that the fraction denoted here by gamma and mu and lambda and mu and gamma, that they all have to be the same. All the same fraction, meaning that they're all divided the same way. That's what concurrent means. So let's start with that. Now we're going to express b to n. That's this median of the triangle b to n. We're going to express that another way. So it's the same as going from b to c and then from c to n. And b to c we have an expression for, and c to n, well, c to n is just half of c to a, and c to a we have an expression for. Okay, that can be found from what we've established at the top. So that's the first median of the triangle, and by simplifying this expression, collecting the vectors, we've got this half of c plus half of a, take away vector b. Alright, let's look at more simplified expressions for the other medians of the triangle, c to g. So vector c to g is a fraction of c to p. The fraction is mu. C to p is the same as going from c to a, c all the way up to a, and then a down to p. And we can see c to a, well, that's given by that, drawn on what we've got up here. A to p is half of a to b, and we know what a to b is. That's negative b to a. Alright, so we can simplify it carefully that way. And what we're going to notice, if we get all these expressions, simplified expressions for all three medians of the triangle, like so, then we want to then be able to try and form a connection between any two of these. Maybe this and this one, or maybe this one and this one. And by forming a connection, we can relate one expression to another expression. And that means we can try and show a point where they intersect. So we've got this. Now let's look at how this was formed. We have a to g, okay, which draws on this working out, and the median is from a down to g. Okay, going from a to g is the same as running from a down to b, and then once we get to b, running across up to g. Okay, so that's what this algebraic expression is. And for each we have expressions. A to b is negative of b to a, so we can draw on that. And then the segment b to g, well, b to g is the same as this fraction of a median that we worked out before. So we can all put it together. So do the substitution and then carefully expand and collect the a, b and c vectors to get all their coefficients nicely. So there's one expression for a to g. Here is another expression for a to g. So we're going to draw on both parts. Okay, that's equation 1 for the line segment from a down to g, and this is equation 2 for the same line segment from a down to g. So let's equate them, the two expressions, and so then we can equate our coefficients of vector a, b and c and see what's equivalent. So let's do that. From equations 1 and 2 that we identified previously, we've got this interesting equation. So all that for vectors a, b and c, well, that's equivalent to this expressions for a, b and c. Now, equating the coefficient. So from the A vector, the coefficient gives us a lambda on 2, take 1, must be equivalent to negative gamma. Alright, and the other one, so therefore by dividing or multiplying by -1 both sides, we get this. So there's a little expression for our gamma. Very good. And then equating from vector B, this part and this part, we form this equation for the coefficients, and so we can transpose that as well. Okay, now essentially we've got two equations that are equal to the same thing, gamma. So let's solve them simultaneously by substitution. Let's equate 1 and 2 together, and we get this equation. And now solve for our lambda, and voila, we get 1.5 times lambda is equal to 1, so that means lambda is 2/3. And that kind of fits, doesn't it? Because if we look at the size, visually, the size of A to G, well, that kind of looks like 2/3, while G down to this midpoint M, yeah, it looks like only about 1/3. So let's take our value of lambda 2/3, substitute that back in to work out what is the other parameter. Okay, gamma. And lo and behold, after the substitution, we see that it is also 2/3. So that means lambda is equal to gamma. Well, that's quite good, because we've shown that the two of the three meridians, median of triangles, are divided the same way. They both have two segments that are 2/3 of the whole. Very good. And by logical extension of that argument, we're able to have the third median. We can conclude that the third median of the triangle is also divided in the same way. So the segment from C to G is also 2/3 of the whole. So the blue parts are all 2/3 in proportion, while the red parts are all 1/3 in proportion. Interesting. And so they are concurrent. Now, let's use what we've established and work out what is point G from the origin. So our vector O to G. Well, going from O to G, well, first we can go O to vector B, and then from B run along to get to G. Okay? So OB plus B to G. Well, OB is vector B. And now B to G, from the previous slide, we've seen that it's just 2/3 of B to N. B to G, well, that's the blue line here, isn't it? That's just 2/3 of the whole lot, B to N. And we know what B to N is. B to N is the same as going from B to C, and then from C up to N. Now C to N is a half segment. It's like a midpoint segment. Okay, there we go. C to N, well, that's going the other direction. That's negative A to N, and we've got an expression for A to N in the previous slide, and that is this half of C take A. And we've put it all together there, and now we've got it in terms of B, C's and A's, and now let's simplify, collect the terms. That's the A coefficient, there's the B, and there's the C coefficient, and it all works out to be 1/3 each, 1/3, 1/3, 1/3. Excellent. So that's really good, and I think we've got it. So finally, therefore, position vector of O to G is 1/3 of vector A plus vector B plus vector C. They are the position vectors from origin to A, origin to B, and origin to C. Okay, well done. Well, I hope you're able to follow that. Please watch it again, and try working through the proof yourself, slowly and surely, in your notebook, and you can try it on the practice exam that I have given you previously. Well done, everyone.